So we're going to quickly review this. Remember, this is a way that all of the NADHs that we made from processes that were not in the mitochondrial matrix, because if it was in the mitochondrial matrix, they could just go directly to what complex? Complex 1. Okay, but this is one of the two ways that we have to effectively get the electrons that we made from the NADHs in the cytosol all the way into that holy of holies of the mitochondria, which is the mitochondrial matrix. And we talked about the fact that this enzyme in particular, there are two different isoforms. There's a cytosolic version of glyceraldehyde phosphate dehydrogenase that takes that NADH and goes from DHAP to glycerol phosphate, and it goes through a transporter. But the mitochondrial version uses FAD. So then it passes electrons on to FADH2. FADH2 goes to which complex of the transport chain? 2. And that's the reason why it can make up to 1.5 instead of 2.5 ATP. In the process of doing so, you get your DHAP back, it can pass through and go back out to the cytosol. That's not the only pathway out there, but that's one of the pathways. Another pathway is called the malate-aspartate. And so once again, we're going to see, we've already started to see a lot of this overlap between the various metabolic pathways. This is one of the reasons, in fact, just yesterday, I guess, was it yesterday? Yeah, yesterday I think it was, that Professor Wagner and I was talking about medications and how we have these weird interactions sometimes. You take a medication for one thing, you can have such drastic side effects. And the reason why is now hopefully you're getting this idea that these metabolic pathways are not mutually exclusive, that they interlock with each other and when you affect one, you can affect others. Okay? So hopefully you're starting to get an appreciation for that. And so with malate-aspartate, we're utilizing malate and aspartate, obviously, that can pass through the membrane, right? So this is found in many different tissues, but especially the kidney, wrong one, I meant to do the highlight, the pointer, kidney, liver, and the heart, because they just have lower concentration of glycerol phosphate, okay? But malate can cross the mitochondrial membrane, but oxaloacetate cannot, because what is aspartate? Oh, I mean, it's amino acid. But what is the alpha keto acid of aspartate? OAA, oxaloacetate, right? And oxaloacetate is related to malate in what metabolic pathway? Citric acid cycle. Okay, and so this is a way that we can actually start to interrelate all of this together. Okay. So if you utilize this shuttle, you can actually make 2.5 ATPs from every NADH, because the electrons from the cytosolic NADH will actually be passed off to electrons and then to make a mitochondrial NADH. Okay, so we've actually seen a lot of this before. It's just starting to put all the players together. I know, it looks a lot, it looks really scary, but in reality, it's not. Don't overthink it. Okay. I'm actually going to start down here.
Yeah, where did you start?
Well, because it's a cycle.
Right.
Sort of like, this isn't faith and duration, but it's sort of like the wedding ring and the bond, and how it goes on and on and on. Yeah. I guess that could be faith and duration, I don't know. All right, so I'm going to start with just the NADH, since in this instance here, we're effectively trying to get the electrons from this NADH in order to make the NADH in here to go on. And what complex will it go on to? Complex 1 to make up to 2.5 ATPs. So let's start with oxaloacetate. Oxaloacetate can be converted into malate. Takes that NADH that we made from glycolysis and other places like, and other processes like that, and that becomes NAD. So it utilizes, what class of enzymes utilize? It's a dehydrogenase. And what dehydrogenase is this? This is malate dehydrogenase. It's just a cytosolic form, but that's malate dehydrogenase, which I don't have enough room to write it all out, but you get the idea, actually. Okay, the malate can then just go through the membrane, and we have on the mitochondrial side, we have malate that becomes oxaloacetate, and you have an NAD plus that becomes an NADH. So what class of enzymes can this be? Dehydrogenase, and what one is it? It's the same one. It's the mitochondrial version. It's malate dehydrogenase, which once again I'm going to abbreviate. And so that NADH goes to complex 1 and makes ATP. But we've got to make sure that we keep the cycle going, because otherwise we would short circuit. So we have oxaloacetate becoming aspartate. At the same time, a glutamate becomes alpha-ketoglutarate. And so if you just look at oxaloacetate and you look at aspartate, what kind of reaction is going on here? It's an aminotransferase. And in particular, what specific aminotransferase is it? This is aspartate aminotransferase, which I'm going to just call it amino-T because I don't have enough room. Alpha-ketoglutarate, glutamate, and aspartate all can go back and forth. Okay, that's why it looks all those arrows, but that's really important. And we've actually already seen aspartate do this in the urea cycle. Remember, the urea cycle had to go between the mitochondrial matrix and the cytosol already. And so now we have aspartate becoming oxaloacetate, alpha-ketoglutarate becoming glutamate by swapping amino groups. And so what? And it's what? It's the same thing. Okay, so that's why it's also aspartate aminotransferase. Okay, but once again, that's aminotransferase. So here, there it is. And technically, they call the cytosolic version cytosolic, the mitochondrial version is mitochondrial. In this instance, they both utilize the same cofactors and stuff. Now, when we talked about the glycerol phosphate shuttle, they didn't. Remember the mitochondrial one, dehydrogenase, it utilized FADH2 versus NADH, which was the cytosol. Okay.
On our exam on Monday, you want us to differentiate cytosolic and mitochondrial?
On this one right here, it doesn't matter to me, since there's not a difference.
Right.
Now, I mean, if I said cytosolic, then I'd expect you to know where it was at.
Right.
But now for the one with glycerol phosphate, it would, because there is a difference.
Mm-hmm.
So in that sense, yes.
Okay.
This is actually just really a review of the semester in some ways to show that how, and we've already seen this before, reality is just to review, to show you that if you start off with glucose and you go all the way through electron transport chain and the oxidative phosphorylation, it depends on which settle system you use to how many ATPs that you get ultimately. If you use the glycerol phosphate shuttle, you make 30 ATPs for every glucose. If you use the malate-aspartate, you make 32. Okay, and so that's, whereas we've already talked about the fact that if you utilize fatty acids, you make even more because the beta oxidation keeps pumping out even more. I don't ask you to memorize all this. This is just to bring it home. It's the bring it home message. Oh, and please note that overall, you don't make NADH or FADH2 because whatever you make, you break down. So it's not like you accumulate them. That's important. We have a very finite amount of NADH and FADH2 around.
For beta oxidation, doesn't it depend on how long the chain is?
Yes. That's why they usually give a standard, like if it's, I think it's anything beyond like 12 or whatever, you're going to make more ATP. All right. Now, Levi actually kind of spoiled this for everybody. What, the last class period back or something? When he asked this question. Because it's when I made my Bambi and Schindler's List kind of thing. There are ways to decouple or uncouple the electron transport chain from oxphos, okay, from making ATP. So then what happens is electron transport chain still continues on, but you don't make ATP. And so there are different ways to do that, but, and the compounds that do this are called uncouplers. Some are naturally occurring, some aren't. But for example, there's a protein, and we'll talk about it in more detail later, called thermogenin, which is primarily in brown adipose tissue, and it's porous. And so my analogy that day, if you remember, was like the Duke especially back whenever I was at Duke, and the Duke football team was so bad. Yes, they had the turnstile, which would be similar to the ATPase, but then right next to it, they just had an open gate where they didn't take tickets or anything. So it's just much easier for people, or the protons in this instance, to walk through the open gate, which this being the open gate here, and completing the cycle. But it's not going to make ATP because it's not going through ATP synthase. Some of the other ones are medicines, like Valinomycin, which is an antibiotic. Okay, gramacydin, you could have some organic compounds that can do similar things to this. Once again, it's perforating the mitochondrial inner membrane. Okay, so oxygen still makes water, but you get no ATP from it. And that's just to show you the pore and how it's pretty big, and things can just go, it's charged, so things can go directly through it. This is Valinomycin.
So that ring, is that ring ATP synthase?
No, this ring is the pore, so you can imagine, hopefully, that this is like looking through the membrane. So the mitochondrial membrane, inner membrane, I should say, is like this. So normally, ATP synthase, if you're looking down it, would be that mushroom top, you'd be looking through, technically you'd be looking through the mushroom stalk, and then the top would be behind it on the other side, But what happens here instead is the protons go through the hole, the open gate, and not go through the turnstile. So you don't make ATP, the protons just go directly through the opening through the membrane.
This is like
Looking through it, like you're looking down. Yeah, they've just turned it on its side so you can look down to see the actual pore. Okay, I actually already pointed this out the other day, but just to go, well, that's really cool. Like, how many can I actually get? I guess 3 is the limit. I'm using all 5 fingers. I meant to use this one so I could make it smaller so we can see everything. Well, it's crooked, but that's okay. So reactive oxygen species just naturally occur as a byproduct because, we're spitting through electrons, not literally, but they're going through so quickly that they can go astray and start to reduce things that shouldn't be reduced. Or we've got coenzyme Q that can interact, in this instance here, with oxygen to make superoxide. Okay, so we have to have ways to get rid of this. Okay, so why? What can happen if we don't get rid of reactive oxygen species? ROSs? You can die. Yes, but how do you die? What's the special characteristic of this right here? Right, and that makes it a, what's that term called when this has one electron? Free radical. And so what it does is it can damage lipids, it damages proteins, it damages nucleic acids, it can damage almost anything out there, right? Because it can go and start attacking things that you don't want attacked because it's not happy. Okay, and I said superoxide. I don't know if I explained that to you. This right here is called superoxide when it's an O2 minus radical. And it can go on to make an hydroxyl radical, which is really bad as well. We actually have a class of enzymes. There's more than one. I know there's at least 8. But I know there's more than one. And they're called superoxide dismutases. Okay? And superoxide dismutases convert superoxide into hydrogen peroxide, which hydrogen peroxide is not necessarily good, but it's better than superoxide. Okay? And they're called SOD enzymes. Then, likewise, the hydrogen peroxide can actually be converted to water, which of course is good for us. And it does so using our good friend glutathione, which we actually talked about glutathione all the way back to last semester, which I'm sure everyone remembers. Glutathione is a small tripeptide, and one of the amino acids of the 3 is a cysteine. And so what happens is that free thiol, that cysteine, is actually used for multiple purposes. One was to help proteins fold correctly. That's why we talked about it last semester. Because, if a protein's got thiols sticking on the outside of it, you have to be careful because otherwise they may form disulfides with each other. And so glutathione helps protect them, okay, by reacting with them and keeping them from going and attacking everything else. Glutathione is also a buffer. It helps with buffering systems, but when the buffers that our body uses. And it's also used here by an enzyme called glutathione peroxidase, which converts hydrogen peroxide into water. Okay, and then likewise we get this back by converting this is a disulfide of glutathione when it's oxidized to reduce it, and there's an enzyme called glutathione reductase that does it at the expense of NADPH. Okay, and so that's just to show you, and this is to show you what it looks like. A little cartoon looking away. Right, but I wanted to point out these superoxide dismutases are so important because of the fact that they combat all of these oxygen radicals. Right? So there are lots and lots of diseases and disease states and phenotypes that are associated with problems and mutations in superoxide dismutase. One is that it's just believed to help with the aging process, hasten the aging process, because as they decrease their activity, then you're going to increase in these reactive oxygen species, and it causes an increase in the aging, what we see as aging. Another one is ALS. What is ALS? Someone know? In fact, I had a really close friend that just died from it this last week. His funeral is on St. Patrick's Day. No. It's Lou Gehrig's disease, who is this? Oh, wait a minute, what happened? Why isn't it going through? I'm pointing to things, and it's recording a video, and you guys have no idea what we're talking about.
It's not recording. The number's not, well.
No, mine recording, I'm on a different page.
Oh.
I don't know what happened. Like, the video is frozen. Here, let me see if I can trick it out. I'm just pointing to Lou Gehrig, thinking it's really obvious the answer's right there. And so, because I'm not looking up there, I'm looking at here, and I'm just talking. And then, by the way, it's recording all of this for all of our fans out there. For all of our fans, as long as they don't get a stalker. Let's see if we can trick it back. Like, why is that still showing that one right there? Let me pause this video. I told you, Lou Gehrig. So I'm thinking, Ronnie, you should know Lou Gehrig. And I'm like, and Brianna's the one that's answering Lou Gehrig's disease. So that's ALS. ALS stands for amyotrophic lateral sclerosis. And it's just the primary cause of it is a mutation in SOD1. And so, does anyone know what happens with ALS? There's actually there's a very famous person who's had ALS now for like 40 years, 30 or 40 years, and has never died. Most people die fairly soon. It's, I can't believe I'm at it. I just forgot his name. He is a theoretical physicist. This is like charades now. So you become paralyzed. You use the loss of all your muscles. They can't speak anymore, and so he speaks with the voice thing. They even had the movie recently that won the Oscar like a year or two back. Eddie Redmayne even won the Oscar portraying him. It's
Is it Stephen Hawking?
Yes.
Stephen Hawking. Okay.
So I'm like, I can't think of his name. You know, they can't tell. You got that one, yeah. So all's well. But yeah, so he's had it since the 70s, and he's survived it. Usually, and most of the time, the way that they die, obviously they have you hook up to a feeding tube because they lose the ability to control their esophagus and things like that. But usually they die from not being able to breathe, okay, because their diaphragm gives out. You can't move your muscles anymore. Okay, but you don't lose your mental acuity. Unlike Alzheimer's and some of the other diseases, you don't lose your mental faculties. Okay, and one of my best friends in high school, her mother also died, by the way, from ALS, but it's still fairly rare. Then we have various neural diseases. Some of them are associated with Down syndrome and things like that can be attributed to SOD diseases. And then certain cancers now are believed. This should make sense, because if you have reactive oxygen species, it increases the likelihood of carcinogenesis occurring.